given to find the time period of this rod which has uniform linear mass density. It is pivoted over here and it is free to move about this point in a vertical circle at a distance L by 2, that is where its center mass is there. It is connected through a spring. This spring is horizontal spring with the wall and the center of mass, and this is its natural length, and this is hanging vertically. Now we wish to find out, if we displace it slightly, then obviously it will be oscillating like this. We have to find what is the time period of these small oscillations. As usual, what we do is, our first step is displace the body by a small angle theta. So we displace this by a small angle theta, very small angle theta, we have displaced it. Right? So this is theta. Over here we see that is now there are two torques which shall be acting. One is because of mg. Earlier mg, that is line of force, was passing through this axis of rotation only, so that's why there was no rotational effect. But when we displace it, then this force has a net torque about this axis, which is equal to, that is torque. We are trying to find what is torque about O. So one is of this force. The torque of this force about this axis is force into perpendicular distance between line of force and acceleration. This is L by 2. This is L by 2. So from here to here, this is going to be L by 2 cos theta, because this is cos theta. So this is from here to here is going to be L by 2 sin theta. So torque of this force is force into perpendicular distance between line of force and acceleration, that is L by 2 sin theta. This is the torque of this force mg about this. Apart from this, now there is extension. This spring has also got extended. Let's say by distance x it has got extended. If this has got extended, so this will apply a force onto this, that is F is equal to kx. It will apply a force in this direction, that is it will apply x is the extension, and this is going to be k into x. But what is the value of x? This x is so small that is almost a straight line, so we need not find any component of this force. It is almost a straight line, and this is part of this circle. This is L by 2, so this arc is part of this circle of radius L by 2. This is radius is L by 2, right? So we know S is equal to r theta. If we use S is equal to r theta, so this length of this arc, that is x, is equal to r. R is what? L by 2. What is theta? L by 2 theta. So x comes out to be L by 2 theta. So torque of this force about O is also trying to move it this way. Torque of mg is trying to move it this way. Torque of this force is also trying to move it this way. So both the torques, they are in a clockwise direction, so they will get added up. So the net torque, which is trying to move the body towards its mean position, is going to be, one is this torque plus torque of this force, that is force is what? Kx. And what is the distance between this and this? It is L by 2. Now also x is equal to L by 2 into theta. So we can put x is equal to L by 2 into theta. So it comes out to be k into L by 2 theta into L by 2 plus mg into L by 2 sin theta. We also know that is for the very small value of theta, sin theta is equal to theta. So we can replace this by sin theta is equal to theta. And this is the net torque. Net torque should be equal to I into alpha. I about what? I about the same axis about which we had found the net torque. We had found all the torques about this axis, so I should also be about this axis, and the I of this rod, which is uniformly massed rod, and over here about a one end passing through its one of the ends and perpendicular to its length is ml square by 3. So this torque is equal to I into alpha, where I is going to be ml square by 3 into alpha. So over here we find that is rest everything is constant. So we can take theta out from here. So alpha is here. So alpha will come out to be alpha. Everything is constant. So theta can be taken out. So something into theta. So alpha comes out to be. So alpha comes out to be something into theta. So this is constant term. You can rearrange it. So alpha comes out to be proportional to theta. Also, when you are taken. Also, when it has moved from here to here, the restoring torque is in this direction, theta has been in this direction, so they are opposite directed. So this means SHM. So from here we can rearrange, so we can use a formula T is equal to 2 pi theta by alpha. We can find the value of theta by alpha from here and we can put it over here to find what is the time period of small amplitude oscillations.